Lewis acids are electron pair acceptors, and Lewis bases are defined as electron pair donors, or I like to think of them as electron pair providers, because often Lewis bases don't actually donate a pair of electrons and that pair of electrons goes bye-bye. They just make a pair of electrons available to another substance. So I like to think of them as electron pair providers, that is, Lewis bases. Here we can see that the hydrogen ion is acting as a Lewis acid because it is accepting the gift of an electron pair which is provided by this Lewis base that we call ammonia. It so happens that these two substances are acting as Bronsted-Lowry species as well, because the one is donating a proton, namely itself, and the other is accepting a proton, acting as a Bronsted-Lowry base. In this case, the Lewis and the Bronsted-Lowry definitions overlap and apply to the same substances. But the Lewis definitions greatly broaden the range of acids and bases because many species other than H-containing ones can accept or provide an electron pair. Here's another example of a reaction between a Lewis acid and a Lewis base. On the reactant side we have boron trifluoride acting as a Lewis acid, accepting the gift of an electron pair, and we have ammonia acting as a Lewis base, providing or donating an electron pair. We should say here that the simple term acid suggests that we are referring to an Arrhenius or a Bronsted-Lowry acid, that is, a hydrogen-containing substance in an aqueous solution. If you are referring to a Lewis acid, then use the term Lewis acid. You might ask, how can I remember what a Lewis acid and a Lewis base are? This isn't necessarily the most strictly true scientific explanation, but it's a good shoot from the hip mnemonic to help you remember. Something's charge will decrease if it acts as an acid. A Bronsted-Lowry acid, for example, donates an H+. If you donate an H+, your charge will drop. In the same sort of way, a Lewis acid accepts an electron pair. If I accept the gift of an electron pair, I'm accepting negative charges. Doesn't my charge go down? In each case, my charge drops, whether I'm acting as a Bronsted-Lowry acid by donating protons or as a Lewis acid by accepting electrons. Similarly, something's charge will increase if it acts as a base. A Bronsted-Lowry base, as we know, accepts protons. If I accept the gift of a proton, my charge is going to go up. On the other hand, if I donate electrons, you can think of them as I'm donating them, I'm giving them away. If I give away some electrons, my charge will increase. Maybe that'll help you remember what a Lewis acid and a Lewis base are. Substances with an incomplete octet, for example BF3, or ones having vacant orbitals, for example the iron 3 ion, often function as Lewis acids. This is why solutions of many metal ions exhibit acidic properties. So let's explain this a little bit. The positive charge on the metal ion attracts or accepts the lone pairs of electrons on the oxygen of a water molecule. This process is hydration, which is the glomming of water molecules onto metal ions. If we have a metal ion in solution, let's say the iron 3 ion, what's going to happen is, because of its charge, the electron pairs on the oxygen atoms of water molecules will be attracted to it. In other words, those oxygens are donating or providing electron pairs, and the iron ion is accepting electron pairs. That iron 3 ion is acting as a Lewis acid, and the water molecules are acting as Lewis bases, providing electron pairs. Cation size and cation charge determine the extent to which pH is affected. Here again we have hydration, that is, water molecules surrounding metal ions, and we can see here that we have a fairly short distance between the centers of charge, which means there's a fairly strong interaction there. When there's a strong interaction, the OH bond becomes more polarized, and if it becomes more polarized, those H's, or one of those H's, are more likely to pop off, and that would make for a stronger acid. For the potassium ion, if a water molecule comes nearby, there's a much larger distance between the centers of charge there, and because of that there is a weaker interaction. The OH bond in the water molecule keeps roughly the same polarity, and the acidity is unaffected. On the left we have water acting as a Lewis base, providing electron pairs. We have the iron 3 ion acting as a Lewis acid, and on the right we have not acting as a Lewis anything.